In general, when we're thinking about permutations and combinations, we're thinking about drawing subsets without replacement. So when you pick out an item from the collection of items that you're dealing with, you can't pick that item again. This represents a lot of real-world scenarios. However, it doesn't actually represent every real-world scenario. There are going to be times where actually you can reuse items over and over again. And so if we want to be able to solve counting problems no matter the situation, we need to be able to think about, well, what are the ways that we can count up our totals if we're doing things with replacement? So traditional combinations and permutations take subsets without replacement. If replacement's allowed, the resulting formulas need to be adjusted. And so what are we thinking about with selections with replacement? Well, normally if we select k items from n, we do so implicitly without replacement. If an item has been selected, it cannot be chosen again. If instead we're selecting with replacement, everything is being altered. So selecting an item from a hat and then replacing it as the canonical example here, right? So if we put a bunch of names in a hat, we draw out a name, right? We read it, maybe that name leaves the hat, which would be without replacement, but maybe we put it back in, we shuffle it up again, and then we can draw it out once more, right? So in that second case, these can be duplicated multiple times, and that's going to change the fundamental problem. So if we're sampling with replacement, we can still be thinking about this as being ordered or unordered, so we'll still have combinations or permutations, but the totals for both of them are going to change. So we have permutations with replacement and combinations with replacement. Now, permutations with replacement actually are quite a more simple approach than even permutations by themselves. So suppose that there are a total of k items or that we want to select from a total of n, but after each selection, the item is replaced, and then we order the items. So we can actually approach this using the product rule for counting. So there are n options for the first draw, but that doesn't change, right? There are n options for the second draw. There are n options for every draw. And so as a result, the total number is just going to be n to the power of k, n times n times n, up k times. Okay, so this follows directly from our product rule for counting, and in a way, it's a little bit simpler than thinking about permutations on their own. So permutations with replacement can be counted by using n to the power of k. Now, what about combinations with replacement? Suppose that we want to select k items from a total of n, but after each selection, the item's replaced. We're not considering the order of the items. Now, it turns out that we can actually write this down using a formula using standard combination. So if we take n plus k minus 1, choose k, that's going to give us the total number here. Now, this formula is a little bit more difficult to work out where it's coming from, and you can try sort of as an exercise in your own regard to think through this and try to make out the argument yourself. But this is going to work sort of no matter the case. Right? This is a less common formula to apply than the n to the power of k, but it will come up from time to time. The idea is that the modification, the reason that we're not just using n choose k and instead we use n plus k minus 1 choose k is because we want to allow for the duplication of choices, right? So even after you've picked out k items or you've picked out k minus 1 items, there's still the possibility that you can pick those out again. Right? So you can pick out the same item over and over and over again, and that's what that k plus or plus k minus 1 is doing there. Right? So you can try to work out where that's coming from exactly yourself, or you can just take this for granted that if you want to perform a combination with replacement, this is the formula that we use. Okay? So oftentimes we're going to see this as with replacement. Sometimes you'll see it with repetition. They mean the same thing. So some examples. Suppose that we have a set of 6-sided dice and we're going to roll them all. If 2 dice are rolled, how many possible unique sets of numbers can be observed? Okay, and so here we're thinking about the sets of numbers, right? We're not thinking about the sequences of numbers. So we're dealing with combinations, right? But of course, if we're rolling 2 dice, they can show the same number. We're not actually removing it. So it's not going to be 6 choose 2 because that would give us how many ways can you pick out 2 unique numbers from 6, right? Instead, we need to use combinations with replacements. And so we take 6 plus 2, k is 2, minus 1, choose 2, and there's going to be 21. So what we're saying here is that if you roll 2 dice, there are actually 21 different combinations of numbers. So if you have a 1 and a 1, you can have a 1 and a 2, but then having a 2 and a 1 is exactly the same thing, right? So there are 21 ways that you can do this. If you roll 4 dice in sequence, how many possible sequences can be observed? So here we actually differentiate 1, 2, 3, and 4 as our different rolls. Right? And remember, you have 6 options at the first roll, 6 options at the second roll, 6 options at the third roll, 6 options at the fourth roll. And so we can multiply all those things together. We're dealing with a permutation with replacement. So n is going to be 6 to the power of 4, 1,296. Okay. Now let's look at a different example here. We have an ice cream store that's serving 5 different flavors of ice cream. How many possible 3-scoop sundaes exist if each scoop can be a different flavor? And so here, right, we're thinking about, is this a permutation or is this a combination? And I would contest that this is going to be a combination, right? The ordering of your 3 scoops does not matter, but you do still need to pick out 3 flavors. However, the flavors can be repeated, right? And so then what we're saying is that we're not trying to do 5, choose 3, which would tell us how many ways can you form a sundae with each flavor being unique. But instead, we need to go 5 plus k, which is 3, minus 1, choose 3, right? And so this is, again, just n plus k minus 1, choose k. Right? That's what we're dealing with here. And if we work this out, then we can solve for our our combinations in this case, right? 5 plus 3 minus 1, choose 3, is 35. So there are 35 different sundaes that you could order here if you're allowed to repeat flavors. Now, suppose that we have a family of 5 that enter the store and they each order a 2-scoop cone. How many different orders are possible if the 2-scoop cone can mix flavors? And so there's actually going to be 2 steps here, right? The first step that we want to know is, well, how many different 2-scoop cones exist, right? And again, we're not doing 5 choose 2, right? Because 5 choose 2 would suggest that we have to take different flavors. Instead, what we're going to be thinking about is going 5 plus 2 minus 1, choose 2, right? And so that's actually going to be 6 choose 2 on our total number of 2-scoop cones. Now, once we know this, right, once we know that there are 6 choose 2, then we have our family of 5 coming in. And of course, if person A orders the same order as person B, and then person C orders something different, right? That's different than if person A had ordered something different and B and C had ordered the same thing, right? The individual's orders actually matter. And so for the second step here, we're actually dealing with a permutation with replacement. We might have people ordering the same thing, but every individual is going to have 6 choose 2 different ways of ordering, right? So we're going to get 6 choose 2 for the first person, 6 choose 2 for the second, for the third, for the fourth, and for the fifth, right? And that's going to give us our total. And so this is sort of the approach to the problem, right? We figure out how many ice cream cones, and then we figure out how many orders from there. One thing to note is that if you considered your ice cream cones with, say, chocolate on top and vanilla on the bottom to be different than a vanilla on top, chocolate on the bottom, then that's going to change this answer slightly. But let's suppose that each cone is a combination with replacement, and so that's 5 plus 2 minus 1, choose 2, or 15 total possibilities. Then the family orders can be thought of as permutations with replacement. So it's 15 to the power of 5, or 759,375 total orders. So if this family goes in, there are 759,375 ways that the 5 of them can order a 2-scoop cone if we allow them to repeat flavors on their 2-scoop cone. So while most of our scenarios described can be sampling without replacement, in the real world, we're oftentimes not going to be replacing items. If items are able to be repeated, then the logic of permutations or combinations has to be adjusted accordingly. And so if we're going to be in a situation where we're putting the names back in the hat, where we're able to duplicate our flavor choices, where we're rolling a die or flipping a coin or doing something that can repeat itself over and over and over again, we need to recognize that the number of total possibilities is going to be different than if you weren't able to do those replacements. Of course, if we're dealing with permutations, we're still thinking about ordering. We have a fairly simple formula for that. If we're dealing with combinations, things are still unordered. The formula is a little bit more involved, but ultimately we're still going to rely upon that formula to count out our totals.